All right, let's go ahead and get started. We have two main topics today that are largely unrelated to each other, but we got to do a little more discussion on the analysis of the feature models and how they map to the code. Then we'll start talking about means of implementing variability in systems. As usual, feel free to ask any questions you have in the chat as we go along, and I'll address them as I see them. So where do we stand after last class? Well, last class we talked about feature models and how they can be translated into these propositional logic formulas based on how we've modeled them and based on the constraints we place between features across the entire tree that's formed. Now, these models can be analyzed based on these formula and based on the selection of features that we choose. And what we want to see in a valid, consistent feature model is that there's at least one selection of features that can be met using the model as you wrote it, right? There's some combination of features that we're allowed to use. Those feature models result in this formula that we've extracted evaluating to true, or these feature selections that we've chosen that are valid. Right? Invalid feature selections falsify this formula and aren't allowed. And SAT solvers can be used to identify valid configurations, either based on a complete feature selection or based on a partial selection where we can then see what remaining choices are available based on what we've chosen so far, right? If no feature selections can be found that are valid, then the model is inconsistent and there's some kind of problem with it. And that core idea that we can take this formula and put in some selections for the features and see what comes out in the end results in all sorts of different analyses we can perform. For example, if we're just interested in checking additional properties of our model, we could select a feature selection and then see what happens when we append the formula from our model with this fact and see if that can be made true using a feature selection. Right? This idea enables all sorts of different ways to look at these models and see whether we formulated them correctly based on the requirements we've had to date. From there, right, we can build our code and test our code, and we can make sure it matches these models, right, and make sure that they're all in alignment with each other. So the main things I want to talk about in terms of analysis for the first half of this class are how we can map the feature models to the code a little bit better. And then I'll look a little bit on ways we can use the same idea of Boolean satisfiability in order to analyze the code. Right, so let's look first at feature to code mappings. Now, in our last class, we focused on the problem space, right? The domain analysis itself, and our breakdown of this into different features that we might select for a particular concrete product later on. Right, so we focus on the problem space with the feature models and the feature selections. Now we're going to move the focus a little bit, and we're going to investigate the mapping of the features to the code we've written itself that actually implements those features. Right, this mapping from the problem space to the solution space where we have these concrete products we're releasing. So by leveraging the same Boolean-based analysis from last time, we can look at how to detect things like unused modules in our code, dead code in preprocessor-based implementations. We can elaborate on issues regarding build systems that can complicate analyses. And so specifically, we'll look at a few things here. Which code fragments are never included in any real product? Which code fragments are being included in every single product we build, meaning that they're not really optional. They are actually used in every product we build. And which features have no influence on our product portfolio? Which features are ones that we never really make use of or can't make use of if our model is too restrictive, right? So our first goal is to find dead code. These are fragments of code that are never included in any valid feature selection. So when you go and build real products from your product line, what are the features that we never make use of, the pieces of code that never get included? So dead code, it could be an indicator of an incorrect mapping or an over-constrained feature model where you have contradictory or too many constraints. If we look at the model and the corresponding code here in this slide, so we have a program with two real features, features A and B, right? Now this is this open fan, right, which means that we're going to choose exactly one of these at any given time, right? And we can see some corresponding code here, and this is this preprocessor-based implementation. I mentioned this once before, or sorry, you mentioned this in earlier lectures before, but basically you put these annotations in the code. This is in C or C++ in this particular form. And this checks to see if you've defined this variable A, but you define each variable for each feature, right? So you have a macro for A, a macro for B. If it's defined, that means we're including the feature. If it's not, that means we're not including the feature. So if we've included the feature, it'll include the code when we compile it between the if def for this and the end if for it, which is actually down here. If we do not include the feature, that code will be absent entirely from our compiled version, right? So as the code is defined for this, lines 2 through 9 are only included if we use feature A. Then within this, lines 4 through 6 are only included if we use feature B. If not, we include line A, right? So if B is being used, this line will have line 5 in there. If it's not, line 8 will be in there. None of this will be in here unless we use feature A. Now you can probably already see some problems with this, right? If we look at the model and we look at the corresponding code, right? Feature line 5 is only included if features A and B are both selected. But our feature model says these are mutually exclusive. It says we can only pick one of these, right? So there's going to be a problem. Our code and our model don't line up with each other in terms of what they say should be happening, right? Line 5 can never be included in any real product in the product line. If you selected both of those in your real system, it would never actually make it in there, right? The developers were likely unaware that features A and B were defined as mutually exclusive in their model. Or our feature model is too strict and both features could technically be optional, or this could be an or where we can have both at the same time, right? There's different ways we could have looked at this, and we probably should have. They probably should not be mutually exclusive because when we went and implemented the code, we said, no, they're not mutually exclusive. So it doesn't actually match our model, right? So we have a bug in our model or our code, and we need to resolve that and bring the two in agreement with each other, as B cannot actually be used without requiring A as well, right? Most likely it's your model that's at fault. By the time you went to implement the code, you probably had a pretty clear idea of what you needed to do, but it could be either, and you want to check both and make sure the right implementation is what lives in the end. There was a question in the chat, what justifies a strong constraint? There are often situations where certain features can't be used in combination with each other, or making certain choices means that certain features get ruled out. If they're in strict hierarchy like this model, you could define that easily in the model, but then often they're in different parts of the tree that gets formed. So you need these cross tree constraints to define these dependencies between different sections of the tree. Sometimes those can get very complex as you have a super complex feature model, like you have a feature that when you use it, it rolls out 12 or 13 other features. And that's not unusual, right? But if you're not careful when you define this, well, now you might have dependencies between some of those individual features in those 12 and 13, where, already in another part of this, you're saying that if you use one of those, you must use another one of those, right? And once these constraints start adding up, it's not even just the one constraint's problematic. It's often that you have multiple constraints that conflict with each other, and you weren't very careful to look for those dependencies between the different constraints, right? And that, in the end, often introduces these contradictions. it's pretty easy when you get a complicated model to accidentally do that. So I hope that addresses your question. If it doesn't, feel free to ask a follow-up. So to identify dead code, we need to reason about the mappings from features to code. Formally, what we can do is we can describe this mapping as a function from our code fragments, right, from the set of all code fragments to sets of products that are represented by feature selections. So what we are doing is we map each code fragment to the set of products where it could be included. Now to do this, we need a compact representation of big sets of feature selections and the corresponding products. And we do this using what are called presence conditions. Presence conditions are propositional formulas that represent a set of feature selections, right? Rather than being one feature selection, they represent a bunch of feature selections. This is in line with the propositional formula we use to represent the set of valid feature selections in the feature model. So a presence condition is a Boolean expression defining the feature selections where a particular code fragment is present. We use this function called PC of C. So this is the presence conditions for a code fragment. This is the conditions for that piece of code to be included in a product. Like what has to happen for that to be true based on our feature model. So for example, we have a code fragment here in line 3. And its presence condition, what must be true based on our model for it to be included in the product. Line 3 specifically is that we're using feature A, right? In line 5, what do we have to do according to our feature model to include the code in line 5? Well, A and B must be used, right? Because it's within this if-def for A. Now we have this if-def for B. What about line 8? To include line 8, there's actually a typo here. That should be not B, right? So for line 8 to be included, B has to not be included. It's the else on that, right? Oh, no, wait, hold on. Sorry, rereading my code here. Okay, no, sorry, it is not A. Line 8 here is the else on this if-def, right? So this closes with this. Sorry about that. So to reiterate in this code, if we're using feature A, line 3 is included. If we're not, line 8 is included. Within this, if we choose it for line 5, if we choose A and B, line 5 is included. Does that make sense? Sorry, so okay, someone said no. What was the no to? Yeah, so you see if-diff is ending the block, right? So if this was the else for B, there would be an end diff after this, and then we actually have two of them to be contained in here, right? So if def opens it, end diff closes it. Anything within it is part of the expressions. So lines 4 through 6 are the block for feature B. Then this else is the else for this. So this would be if else on that in a traditional if block. Does that clear it up? Okay, cool. At least for the one person in the chat. So I misread that earlier. That can get a little confusing. So okay, revisiting this, the presence conditions are the conditions that have to be true for the piece of code to be included in the product defined by our model. So line 3 is A. Yeah, they behave like nested if statements. Yeah, they absolutely do. Line 5 is there if it's A and B. Line 8 is after this else, right? So if we're not including A, then we include line 8. So that's not A. Hopefully that clears that up a little bit. Now we can do this also for not just one line. This can be any arbitrary segment of code, right? So, well, what about lines 3 through 5? Well, that would be A and B also, because that's the combination of conditions to get to this point. What if we wanted to, just say what are the conditions for this whole thing from line 3 through 8? Well, that would be A and B and not A because of this line, right? And that's contradictory. So that means that we can't have this whole segment line 3 through 8 in our product. Okay. And that's impossible to meet, so that can't be included. And we can look at subsets of this that can. Okay, there's a question. So if A, if B, I think we might be saying the same thing. So all right, so let's see. End if would be kind of like closing the brackets on the if statement, right? So basically, yeah. So this if def closes the end if closes this whole thing, right? But this else is if we don't include A. So this would be like a nested statement within this. This would be just an if B, and we don't have an else on the B part. So let's see. I'm going to throw this into the chat. If A. All right. Let's see. Let's give that to everyone here. All right. Sorry for the confusion. If A. So it's hard to do indentation in the chat. So I hope everyone sees that. Basically, we have, right, line 3 is, if A is true. Then within that, we have a nested if B. If B is true, line 5. We don't do anything if B is false. And then there's this else, which is if A is false, we do line 8. So hopefully that makes it a bit clearer. In any case, we'll have some more examples of this a bit later on. So a code fragment is dead if it's never included in any product in the product line. So since the representation of the feature model as this propositional formula represents all the valid feature selections, all the valid products we can build, a code fragment is dead if the conjunction of that presence condition and the formula describing the feature model is not satisfiable. If we can't find a set of features that meets both the presence condition for that segment of code and the feature model, then as long as we've implemented everything in accordance with the feature model, then that bit of code will never be included. There's no feature selection that's both valid according to the model and that meets the presence conditions to include that code, right? So in our example, we had the presence conditions of A and B, and not A for lines 1, 3, 5, and 8, respectively. So the predicate of the feature model is the program and A or B, right? Because of this, and not A and B. We can only choose one of these. That's what our feature model says, right? Line 5 is considered dead code because we can't actually satisfy both the formula from the feature model and the presence conditions to include line 5, which are A and B, right? Those contradict each other, not A and B at the same time. So line 5 can never actually be included if according to our feature model. So in a similar way then to how we went in last class when we talked about identifying valid feature selections and testing facts about our code or about our model and whether the model actually meets those facts. We can also detect code fragments that are included in all products as well, right? code fragments, they're mandatory, no matter what they get included. So code fragment is mandatory if and only if the propositional formula representing the feature model implies that the presence condition is true. Right. So in other words, if we go to our SAT solver and we ask our SAT solver to find us a solution that satisfies the feature model and does not meet the presence conditions, and if it comes back and says, no, there's no way to do this, that means it's a piece of code that's always going to be included, right? According to our model, this piece of code will be in every single product we ever choose. So we have this graph library example we went through last time, and we have this propositional formula for it. And as long as the code is implemented correctly, this edge type feature will always be there. And we mark it as a mandatory feature in our model, right? So that's pretty easy. So we could ask the SAT solver to come back and look for the code that represents this edge type feature, and it should say that it is there when we go and look at the presence conditions in the code and match that with the model. Does this idea make sense? Right, any questions so far? I also want to make sure, especially with the bit of confusion over the code example there, the idea is okay, right? But basically, we're taking code fragment that's related to a feature, going to our model and asking, hey, when should this be included, and matching it up with when our code says it should be included, and seeing if that mapping matches up, right? If the model says it should be there and the code conditions for it being there are in line with each other, then we're in good shape. If we're not, there's a problem either in our code or our model, and we need to fix that. All right, so let's take this one step further, and let's apply some of the same ideas to look at our code itself and how we can analyze that source code. Okay. So after we analyze the feature models and we analyze the mapping from the features to the code, we're now left looking at the variability in the code itself and how that functions, and the program structures like the function calls and the statements within the code itself. These are what we call these variability-aware analyses because they perform traditional analyses like type checking or model checking, but they incorporate knowledge about the variability in the code itself. So again, what we want to do is we want to analyze and we want to ensure that the properties for all of the possible product lines are accounted for. We don't want to look at individual products one at a time, but what we want to do is look at variability across the entire product line and make sure that regardless of the configuration, that the properties we're interested in are being obeyed, right? So there's some analyses we can build on top of the same kind we've been presenting last class and early in the past few minutes, and look at different kinds of domain engineering artifacts, our feature models, our implementations themselves, and the mapping between them. So the idea of a variability-aware analysis is not necessarily to invent new kinds of analysis techniques, but to lift existing analysis techniques developed for individual programs to the entire product line, like to our reusable assets or domain artifacts. So some types of analysis you might want to perform across the entire product line include things like type checking, making sure that the code is used as expected based on the data type it follows. Flow of data and how data can flow between different parts of the code, and verification of facts across the product line. Memory management, deadlock, concurrency issues. Those are the type of things we might want to analyze. So the idea would be to perform the same type of analysis on the product line that we could perform on every possible individual product separately. So ideally, a variability-aware analysis would yield the same results as analysis for every single individual product, but in a more efficient way, where we don't have to actually go and check every possible concrete product, right? A variability-aware analysis should give the same result as applying existing analysis on every single product, but should be much faster by only really looking at how variability is encoded in the system. For example, if we have a bunch of products that share code, then an analysis of variability over them might only have to analyze that code once and not over and over again for every feature selection it's included in. So that's a lot of rambling. Where does it make sense? Well, one illustration of how we can apply this kind of Boolean satisfiability based analysis is with type checking. It's a pretty well understood problem. It's easier to explain than some of the others, but the same ideas we've been presenting would work for other analyses of other properties we might be interested in too. But in any case, type checking is the process of verifying and enforcing the constraints of a given data type. So if a variable is used as an integer, is it in the proper format to be used in that manner, right? Is it actually a string? Is it actually something else that shouldn't be forced to be used as an integer? If we call a method, does it return the right kind of data? Right? If we assume a method returns an integer, is it returning an integer to us? This is something that kind of analysis is something that can occur either at compile time, so statically, or when we're running the code or dynamically. But type checking in any case is all about ensuring that the program is type safe, meaning that the possibility of type errors is kept to a minimum, right? But the same kind of analysis that we'll do for type checking can also be performed for other properties as well. So there is a pretty large design space of different analyses, and developers have explored all sorts of different ways we can make sure programs work correctly. So before we go into like some of the specifics, there's some terminology we want to look at that helps distinguish different variability-aware analyses in the design space. So first, different kinds of analysis are going to check different properties and give different guarantees back to us. So for example, a type system that checks well typedness of programs to ensure the absence of a certain class of errors, while model checking is a different kind of analysis. Model checking takes a summary of information and verifies that the behavior of that satisfies a given specification. So last time we talked about how you could take a property you're interested in and append it to the equation that you've extracted from a model, and then see if there's a assignment to the model that satisfies that property or not. That's essentially what model checking is, where it takes some description of behavior and checks if properties of interest hold over it. In the product line context, the issue arises of how to specify the expected behavior of a product line, right? Because now you're not talking about one product, you're talking about groups of products. Can we specify the behavior of every feature in isolation? Should we provide a specification per individual product? Or is it enough to have a single global specification of all products and how certain facets of them should behave regardless of the situation? For simplicity's sake, today we're going to expect just a global specification that must hold for all products, like all products are well typed. There'll be no null pointer exceptions during the execution of the product, that kind of thing. Finally, there's different strategies that lift analyses to handle the large configuration space of product lines. And so we can say that a variability-aware analysis is a complete analysis if it finds the same property violations that a brute force approach would, that tried every single possible concrete product. We can say an analysis is sound then if every time you find a violation of a property, it's also a violation in if we find a property violation in our reusable assets, in any one of them, it's also going to be a problem in every concrete product that includes that asset, right? So complete and sound are terms you often hear thrown around for analysis. In our case, we say that the approach is complete if the approach over the product line gives the same answer for this combined approach that it would for every single individual product. And we say it's sound that if it says there's a problem in a reusable asset, it's a problem no matter which artifact we include that asset in. So a brute force approach where we check every possible concrete product for violations is not generally possible. There's just too many possibilities. So the first approach we might take, which is easy to apply, is to check only a subset of the products with a normal single product analysis and then hope that holds over everything else. So we could choose, for example, we could choose interesting feature selections, and we could derive the corresponding products from there and just simply compile those or use runtime detection mechanisms to find type errors in the sampled products. And we don't check every single possible product, but we try and cover some reasonably interesting subset of those. The main question here is, how do you select that sample? How many is appropriate? How do you decide what is the subset to look at? And that's not easy to answer, but typically we only want to check a small number of products, but achieve a high coverage according to some criterion. And there's different ways we can do this. One thing is we could just look at a simple coverage of our features, of our feature model, and select products so every single individual feature is included at least once. That's pretty easy, pretty straightforward, right? We just make sure every asset, every feature is included at least once. We could extend this to feature code coverage, where we select products so every code fragment is included in at least one product, right? So just make sure that we cover the source code at least once. A more common approach is what's called pairwise feature coverage, where we try and cover every pair of features based on the different choices, different points where we make these selections of features. And we try and make sure that every pair of features is included in at least one product. Additionally, we could demand that for every feature pair, there's a product with the F but not G, or G but not F between features F and G, in addition to a product that has both F and G in it. And this can be extended to more than just pairs of features, but different numbers like triplets of features or combinations of 4 features, right? Up to a limit of however many we want to include. A couple of others are, we could look at the products that are popular with our customers, those that are chosen frequently, or products with features that are often requested, and focus specifically on those. We also might have domain specific subsets of products that we try and analyze, right? Where we know for that particular domain that there's certain critical features, like in our database system, we might have transaction management is something we choose to focus on. Sampling with feature coverage alone, right, just try every feature at least once, may result in poor detection of errors, because a lot of problems come from the interactions between multiple features. We'll talk a lot more about this when it comes to testing, right? Where a lot of issues that arise when you build concrete products out of these reusable assets is that certain features won't work well together, even though in theory they should be fine. But errors emerge when they start to interact with each other. The same thing is true when we're looking at analyzing our product lines, right? Certain features may not play well together. Pairwise coverage is an attempt to address that problem by analyzing every pair of features. So we detect at least the interactions between 2 features. Things can still go weird when you have interactions between 3 or more features, but that's rare. Most issues are just between 2 features. So we can cover all pairs of features with a reasonably small number of samples. So for example, a feature model that had 88 features can be covered by 40 products, that capture the different pairs of features that occur. A model with 287 features could be covered in 62 products, right? So instead of analyzing 287, we can analyze 62 that are chosen carefully to cover those pairs of interactions. Pairwise coverage is generally the basis for testing of product lines and other systems that make heavy use of variability. Because we can't possibly try every combination of options, but this gives us a nice balance between detection of feature interaction problems and the number of test cases or analyses you perform. Right. Now, these sampling strategies are sound. If they detect a problem, it's always a problem, regardless of the concrete product you perform or that you derive. but they're not complete, right? Because you haven't tried every combination of features. You haven't tried every single possible concrete product. Since we're not looking at all products, we might miss errors. We can't establish guarantees for the entire product line, but when we find an error, we're sure it's actually an error, so it's a starting point. That was basically just a long-winded way of saying that this is a really expensive process. So what we wanted to do is either find a cheap way to capture information about all products, or we want to intelligently sample from the set of products because we can't possibly check everything, right? So let's look at an example of how we would analyze an entire product line using a similar approach to what we talked about for analyzing the models themselves and then the mapping between the code and the models. So we can look at what's called family-based type checking. We can look at this in the terms of these preprocessor-based implementations with these if-defs, and we'll keep talking about that as we get into implementation, right? So again, this is where we include special annotations in the code, and the compiler is going to look at those and decide what to actually compile into the product. The compiler reads these annotations in when parsing the code, but only includes the code fragments in the compiled binary based on our selected features, right? So we have some code here for this class. The compiler is going to read through these, and this is more of a Java E format. Like this isn't the strict C and C++, but it's just an example. It's going to go through and it's going to check these. And if we've included the name feature, for instance, lines 5 and 6 will be included. If we included no name as a feature, line 9 will be included. Line 12 will be included if we include the feature color. Further down, line 18 is only there if we have color and name, right? And this color class is only included if we use the feature colors, right? So the code that gets compiled in only includes the features we've said that we are explicitly including, right? So what this means is nodes can optionally have a name in addition to their ID. So if we use this feature, nodes have both an ID and a name, which adds a getName method. If we are not including the feature name, our model says we're going to have this feature no name, right? Which still means we have a method for getName, but it's just going to return a default value based on the ID rather than the name we've assigned. Together with the feature color, our example has 3 features, right? So name, no name, and color, and they can be combined to form up to 8 different products. For some of those products, the Java compiler is going to issue a type error, right? If we select neither name or no name, if we say no to either both of those, that's going to lead to a dangling method invocation in the parameters of the print statement on line 20, right? So it prints based on getName. There's going to be a problem there if we select neither of those, and there is no method with that name. Does that make sense, right? Selecting both name and no name is going to lead to this method getting declared twice with the same signature, which is going to be a problem. So there's an issue if we try to include both of those, right? So to detect those kind of errors with a brute force approach, we'd have to derive and then try compiling all 8 products. That's not a big deal, 8 products, but this is a simple example, right? For this example, we could try all 8 products and see what happens. And then we could identify both of those errors where we use name and no name, or the error when we use neither of them. But that's not going to scale to a larger product line. Like this little bit of code is going to have 8 times that you compile this code, right? Oh, someone just said in the chat, oh, is it possible to implement else if? Yes, it is. Okay, yeah, someone replied with this elif as in, yeah. And we'll have some more examples of that. We're going to talk a little bit about how this is implemented in both GCC and a couple of different Java-based versions of it later on. But we can use Java's type system then to take this variability into account. So what we want to do is reason about the presence conditions in the source code. In contrast to the presence conditions for just arbitrary type fragments, like we talked about a few slides back, Now we want to look at the presence conditions for specifically structural program elements, so variables, fields, and methods. In our example, there's two methods here that are getName, right? They both, so in line 6, we have a method getName. The presence condition in this case is that name is true, that we use that feature. The version in line 9 of getName has the condition no name, right? Just for when we include that. Not too bad. What about this line 18, right? Well, that has the condition that we're using the features color and name in our feature selection, right? Not too bad. Okay, what about line 20 to get to this point, where we call system.out.print getName, right? It isn't within an indef, ifdef. So we should be able to include that, right? That's not a problem, but it does get complicated because it calls getName, right? And so we inherit from here that we must have some version of that method defined, right? And so it's going to be either name or no name, right? Are really our two possibilities. It leads to a condition that one of those needs to be set. Right? And this gets complicated. We can kind of emphasize this mapping of presence conditions to program elements by looking at the abstract syntax tree of the code fragment that includes nodes for variability, as the optional nodes are points where we have variability, which indicate optional subtrees in our call graph with a presence condition. And this shows us the program flow between different elements. So for instance, we have ID. ID is a field of type int. It's initialized to 0, right? And you don't need to be an expert on these. This is really just to kind of show how information flows through this little bit of code. If name is set, we're going to declare a field type, a field called name of type string, right? We declare a method getName here of type string. It's going to return a field access to this.name, right? So you can basically just see the flow of information through this program. An analysis of this is going to operate on a program representation that is itself variable. So in our example, type checking takes place on this variable abstract syntax tree that represents the whole space of possible products, what we had on this previous slide. We want to analyze over this to identify whether the information we're passing around is of the right format to be used, and that when we call a method, we're actually going to be able to call a method and get the right information back from it. So when we're resolving a method invocation, there can be different target declarations in different products that we can build in our product line, right? We have two versions of getName, the getName method in this example. The type system has to ensure that all of the deliverable products that contain the method invocation also contain a corresponding method declaration as a target with an expected type. So there has to be a method to call of that name with the expected data type. So in our example, the method getName is invoked in all products, right? With the presence condition true. We are going to call it when this line 20 is called. The print statement on line 20 is always included, so getName is always being called at some point. And that statement is expected to return the type string when you call this method, but the corresponding method declaration is only present in products with the features name or no name, lines 6 and 9, right? And both of those return type string. So just by comparing the presence conditions within the product line implementation, we can identify that products without feature name and without no name are going to contain a type error, right? We're going to eventually call getName. If neither of those are included, then we have a problem. If our feature model says that that's okay, if our feature model says that it'd be fine to have neither of those, then there's an issue. Then we want to be able to identify that issue, right? Then if our feature model says we can have both, our analysis of the code can issue an error message saying, hey, well, we can't resolve get name in line 20, right? If we have this feature selection, then we can't figure out what to call, right? Similarly, if our model says we can have both name and no name defined, well, then we also have a problem, right? Because then we have these dueling method declarations. And if our model says that's okay, and we select that, then we can come back from our code and identify, hey, there's a problem here, right? Does that make sense? Are there any questions so far? I've just been rambling endlessly. Okay. So a type system is going to perform lookups of fields, of local variables, of methods, classes, types, and so on. In all cases, we need to ensure that the target element that we're looking up is present whenever the source element is present for a call. And often there are additional constraints we add based on the data type. So for example, a field can only have the type color, and we can only instantiate class color when there's a corresponding class definition for the class color present, when it's actually declared. Or generically, if we have a feature model, which has a propositional formula it defines, if we have a presence condition, we have a source element in our code, and we have a set of target elements that are called from that source, then we can formulate a generic constraint, which we call the reachability condition. The feature model, right, if the feature model is true, valid, right, if our feature selection is valid, and that implies the presence conditions for the source code are valid, which in turn should imply for each of the targets called from that source that the presence conditions are also met for those targets. Right, so when the feature model is satisfied by our selection, that implies the presence conditions on the source are met, that the source code is there, and that anything called from that source code, the targets, also are present. If that's not true, if we can negate this and get a solution back from our SAT solver that says, hey, that isn't being met, then we can report an error message indicating that there are products in our product line that don't compile because there's not a valid target to call, right? So in that last slide, right, we had, this line 20 is going to call get name. If our product line comes back and says that, hey, you can have a case where neither of those are being used, but our code is now going to have a problem, right? We're going to have a violation because our code can't call anything. Right, then we can report this error message indicating there are products in our product line that don't compile because they don't have a valid target to call. We can use a SAT solver to perform this analysis, right? We plug in this equation, we negate it, we say, give me something that violates it, and it's going to see if it can violate this particular expression, right? It can find a feature selection for which the source code does not have a valid target to call. We can even pinpoint the error message to a set of feature selections here by feeding in this negated constraint. It'll come back and find a violation for us, and we can present that to the developer and say, look, there's a problem here, right? So for example, here's the complete set of reachability conditions for this particular example. If we can satisfy the negation of any of these, there's a problem in our feature model, as there's no valid target for a call from the source. So for example, in line 5, we declare a name variable, right? So in line 5, we declare this variable name. Now the target of that call is the Java standard library. We know that target is going to exist. So our constraint just notes the getting to this line implies that we need to be using the feature name, right? So if it is, then the full constraint is met. Name implies true. Now in line 20, right? So in line 20, system.out.print get name. In line 20, there's this call to get name to either 6 or 9, which implies at least one of the either name or no name must be set, adding a constraint. And by solving the constraints, we can see that without additional restrictions from the feature model, 2 constraints are being violated. So we can report those as error messages to developers with the line number and the reason, right? This isn't just an example, though, of the type of analysis you can perform on your product line between the code and based on information you also define in your feature model. The same approach can be applied to other forms of analysis over our product line as well, right? And there's a whole range of things we can do by thinking of this in terms of logical expressions and looking for assignments to the feature model that violate the properties that we're interested in, right? But a general strategy is to perform analysis on shared code assets only once, and to reason about the entire configuration space using propositional formulas and SAT solvers. So to summarize what we've been talking about last class and so far in this one, right, we have these feature models which can be translated into propositional Boolean logic formulas based on the model itself and based on the constraints we apply. Valid feature selections satisfy the formula we extract from the model, and invalid ones do not, right? And from the same model, we can keep adding on additional information, passing that to a SAT solver, and it's going to try and find violations of this. And when it does, it reports them, right? Within the feature models, we can check whether properties of the models are true. We can look for dead or mandatory features, features that are either never or always included. And we can look at the effects of partial feature selections based on what we've chosen so far. Which features can we choose? Which ones can we not? We can look for code fragments that are either never used or always used by mapping the model to the source code. And then we can look at the code alone and see if within the code, when we call an element of the code which is controlled by the variability, controlled by the feature selection, will it actually work? Will there be code that gets called, and does it return the data type and data values we expect? Are there any questions on any of this? Right. Feel free to ask in the chat. What we're going to do is let's go ahead and just take a 5-minute break. Let's come back at 2:11 and we'll continue with the next topic. All right, there's some people asking about a longer break in the chat. Mainly, I was saying having a short break because we have a fair amount still to cover. Let's just take a 10-minute break now. And if we have some more time later on, we'll take in a couple additional minutes. But let's come back at about 2:18. Let's give that about 10 to 15 minutes, right? We have a lot more I want to make sure we have time to cover today. All right, let's go ahead and get back into it. And go ahead and talk about the next topic because we have a bunch of things that we want to make sure we cover today. There was one note about asking about 2 shorter breaks. I often try and actually do 2 shorter breaks, but today we're just going to have the one just to make sure we cover everything. Other times it depends on when we have natural breaks. But yeah, let's get back into it. So we're going to start moving away from the feature models a little more now and moving toward how you actually talk about implementing variability in your source code itself. This class, next class, we're going to talk about actually having your code make use of these assets. We're going to move further into architecture as we get into the classes after that. And then the final couple of lectures are going to deal with how we test the final system. So we're going to be talking a lot more about the actual code starting at this point. To implement your product lines efficiently, the underlying code has to be itself variable. And variability is a very general concept. So to make this more specific, we're going to define variability specifically as the ability to derive different products from a common code base of assets. Software design is driven by the needs of its stakeholders, which are manifested in features they want to see in a product. So instead of serving the needs of one particular stakeholder by developing a product from scratch, software that is designed to be variable can be tailored to stakeholder requirements by them selecting from the set of options. And now, when we talk about implementation, there's 3 dimensions that we're going to consider in looking at how we can define a technique for implementation. And these are what we call the binding time, the technology we use, and the representation. And let's introduce each of those in more detail, and then look at some specific ways that we can take those assets and produce complete customized software, right? So the rest of today, we're going to talk about some basic implementation concepts, right? And then talk about the 2 simplest forms of implementing variability, which are using preprocessors and using configuration parameters, right? Then next class we'll getting more complicated by talking about implementing using design patterns, and then after that we'll get into other techniques as well using frameworks and components. Right, so when we derive a product, we make a set of decisions. We decide which features will be included in the product or not. So we say that we bind a decision. Different implementation techniques allow binding decisions at different times. Right? When do we decide which assets to include? We have different options. We have compile time binding or static binding, static variability. We have load time binding, and we have runtime binding, which is also called dynamic variability. So with an implementation technique that supports compile time binding, developers make decisions of which features to include at or before the time the code is compiled. When we invoke the compiler, the code of deselected features is removed and not even included in our final product, which gives us this fast, lean executable that only includes the set of features that we decided on when we compiled that code. We've seen a couple of examples now using those if-defs in C and C++, and where we use preprocessors. We use notes we leave in the code, and those annotations determine what to compile. With an implementation technique that enables load time binding, developers can defer feature selection until the program is started. So when we start, so the executable has everything in it, but when we run the program, we give it some information from the command line or from a configuration file or some source that says, all right, when you run it this time, here's what you should do. Here's the options you should enable. So during compilation, all variations are still available. They're decided after deployment through, for instance, through command line parameters, through configuration files. And then runtime binding is where we can change the configuration of the system when it's actively running, right? During program execution, we make decisions about which features we want to enable. So we trigger reconfiguration through either inputs or internal or external input through method calls or through API parameters. For instance, you could send a post request, and in that post request, you could include a set of options, which will then change how the program runs when it takes in that post request. Some implementation techniques support multiple binding times. There are some where you can set certain options at runtime or at load time, right? So the different binding times each have their own advantages and disadvantages. Typically, compile time binding is going to leave room for a lot of optimization. It's going to remove all the unnecessary code from the product, which is going to reduce the runtime overhead in terms of your memory consumption, in terms of your execution time and your binary footprint. However, the trade-off here is that once the product's been generated and deployed, you lose any ability to customize it further or any ability to change it without going back and compiling again and sending out a new executable, right? So what this generally means is that your customer can't make any changes to it unless they come to you and ask you to give them a new binary to work with. A product with load time variability is much more flexible to reconfigure. Instead of recompiling a new product after every change, the end user can just change their command line parameters. They could change a configuration file, however you make these decisions, and then restart the application and get the result they wanted. And then a product with runtime binding, where you're delaying the variability decisions to the point where the program is running, is going to have the most options for changing it. You can even change its behavior while you're running it. Instead of recompiling a new product after every change, right? Or instead of having to restart the program can react immediately and change its configuration on request. That gives you the ultimate flexibility, but the mechanisms for load and runtime binding often have performance overhead and often require more memory to run, since all the variations are being compiled into a single executable. And you need some extra code in there to make sure that the right options are getting called at the right time, right? Including unnecessary functionality in your shipped product can also be considered a potential security threat, right? It can lead to undesired feature interactions, and it requires much more careful testing, right? So there's a trade-off to make. The fewer features you have in the executable, the less configuration in the executable, the faster it's going to be, the more secure it's going to be, the less testing you have to do, the more you can expect it to just work, but that loses any ability to make further changes to it later on, right? So that you have to decide where you stand on that trade-off. The second choice we make is in terms of the technologies we use to implement variability. Technology-wise, there's really two main routes we can take. There are those that we implement using the mechanisms provided by the programming language itself, called language-based approaches, and those that are based in the tools that operate on artifacts externally to derive products. We call those tool-based approaches. So a language-based approach is going to use the mechanisms provided by the host programming language itself to implement the features and derive the products. Method calls, if statements, class design, those kind of things. A tool-based approach uses external tools to implement or represent features in the code and control the product derivation process. Right. A tool-based approach might go through and comment out code that you're not going to include in your executable. Or it might be a build system that selects plugins when you go to compile the code and switches them out based on the choices you've made. A tool-based approach might use the version control system to only check out a particular version of the code that fits the specific feature choices you've made, right? Now, you can't always draw a sharp line between language and tool-based approaches, but it's a rough distinction that gives us ability to contrast these different techniques with each other. In a language-based approach, both the implementation of the features as well as the feature and variability management itself are located in the source code. That makes it easy for developers and analysis tools to understand and reason about the product line and its implementation on the whole. But depending on the implementation approach, feature boundaries and feature management tend to vanish a little bit in the code. For example, you might have to find a particular if statement somewhere in the code that determines which class gets called, right? A tool-based approach ideally is going to favor a clear separation between the implementation on one hand and variability management and product derivation on the other. And that can simplify the code structure at times, but it also makes it necessary for developers and the tools you're running to locate, to understand, to reason about different artifacts in different places, right? So again, there's a trade-off to be made. Now, our third factor is about the representation of variability. A major goal in product line engineering is to derive a product automatically from the variable code based on the user's feature selection. So product derivation is going to involve generating concrete products either statically or dynamically. And there are two main ways to represent variability and the variation points and how products can be generated, which are called annotation-based and composition-based approaches. In an annotation-based approach, the code of all features is merged into a single code base, and we mark that code with annotations as to which code belongs to which features. That's like the preprocessor approach we've talked about a couple of times, right? Where you mark within the code that, hey, these lines are associated with this feature, and these lines are associated with this other feature. An annotation can also be code-based, right? It doesn't have to be something used externally, but it could be something like an if statement as a form of annotation. An if statement saying, if this feature is enabled, run this code, right? So during product derivation, all the code that belongs to deselected features or invalid feature combinations is going to either be ignored at runtime or removed at compile time to form the final product based on what these annotations say should be done. Annotation-based approaches are pretty widely used in practice because they focus mainly, and they are what we focus on mainly when we talk about implementation, because they're easy to use. They're already natively supported by programming environments. I mean, an if statement is already part of the language itself. However, some of these implementations based on annotations are also criticized for their potential complexity and lack of modularity, because often the code for multiple features is merged into a single class or a single file, which makes it hard to separate. It makes it hard to understand which code is going to be included at a specific time. By contrast, we have composition-based approaches, and what these do is they locate the code belonging to a feature or a combination of features in a unit of some kind, in a dedicated class at minimum, or a dedicated file, but maybe even an entirely separate service or package or module that you import somehow. So code for features is separated and independent, and then you have some glue code that connects in the right plugins. Right, so a classic example is a framework that can be extended with new developer-written plugins, and one plugin per feature, and products are generated by integrating the right plugins, either when you compile or when you run. So the key challenge of composition-based approaches then is to keep the mapping between features and the actual code implementing them nice and simple, ideally one-to-one. You have a class named after this feature, and it is specifically the implementation of that feature. If every feature has its own implementation in the form of just a nice single independent unit, then you can generate a concrete product by simply including the right units whenever you select that feature, with code designed to work independently when you plug in different options. Right. Now, in practice, you might have a combination of these. I mean, you often have some glue code which has if statements, which are technically annotations, even if you're calling independent plugins, right? But we could decompose the system into these composable units where certain components are themselves variable in the sense their implementations are annotated. And you're just going to, you could have an approach where the code that's annotated and for features that are deselected gets compiled out, just gets ignored and removed. And we only include the final elements we need, but we still have the code structured in a way that's more composition based, where we have independent code units for different features. But a way to think about this is that annotation is a form of negative variability. We remove code on demand, whereas composition is positive variability. It's the idea that we can add code on demand whenever we ask for this code to be incorporated, right? And often, like I said, the line between these is a bit fuzzy. But the rest of this class and next class, we're going to talk about 3 examples, and then we'll continue on with more from there, right? But there are three core examples we're going to talk about are preprocessor-based implementations, parameter-based implementations, and design pattern-based implementations. Preprocessors are a compile time approach, right? So we decide what to include or not include when we compile the code. It's a tool-based approach. External tools operate on the code itself, and it's annotation-based. We leave notes within the code about, well, what do we want to include or what do we want to ignore. Parameters are a load or runtime-based approach. That's just within the code itself. We have marked in here the points where we're going to swap between different options, right? We pass a set of parameters either to the program when we run it through the command line, or through a method call or through an API call. We decide what to run either when the program is loaded or we reconfigure it during runtime. This uses language-based mechanisms. It uses the structures of the programming language itself to implement it, and is annotation-based because we leave, again, notes in the code, generally through if statements or through method definitions, where we decide what to run. The third design patterns that we'll talk about all next class, right, is a load or runtime-based approach. Again, when we run, either when we send information through the command line, or more often when we call the code when we're running it, we decide what to incorporate and include. Design patterns are often great because they allow you to structure the program in the way that's easy to change at runtime, to swap in different options. Design patterns make use of the capabilities of the language itself, again, class structuring, source code, and are composition based, right? The idea in design patterns is that we design the code as largely independent units that can be swapped in freely. And let's talk more about each of these. So first of all, preprocessor based implementations. Preprocessors, we've touched on this before, but just to go into a bit more detail, preprocessors are tools that manipulate the source code before we compile it, with the intent that we can optimize the final executable in some form, whether that's for speed or, in our case, to configure the executable for a particular use based on the options that have been chosen. The most famous of these is CPP, or the C preprocessor, right? And this is used in a lot of cases as the way that you compile C or C++ code. Most of these examples we've seen are using CPP or something like that so far. And CPP provides directives to inline files, to define macros, and to remove code fragments based on user-defined conditions. Now, in addition to CPP, other preprocessors exist, and we'll talk about, for example, Intenna is a preprocessor for Java. These are important in variable system development because preprocessors usually give us ways to provide this idea of conditional compilation, where marked code fragments go into the final product, and those that are not selected just get removed entirely from the product, right? Conditional compilation is probably the most common mechanism for implementing variability in product lines in industrial practice. So, if you go and work at Volvo, for example, Volvo works heavily in product line development, where the same code base is used across every single vehicle model that's built, right? That code is generally written in C or C++ because we're talking about often embedded or low-powered systems. And within that, preprocessor directives are used pretty heavily to decide what gets compiled in, because the size of your executable and the memory constraints that are super important in embedded system development, right? And so if you can produce a super optimized, super tiny executable, then you're going to have something that's going to work better in the strong performance constraints of embedded systems. Okay. So this is our prototypical example of a tool-based approach. It's using external tools rather than the language mechanisms. Even in CPP, that's an external tool that's going to read over the code and then manipulate it before compiling it. It's compile time, right? So when you compile the code is when choices are made and when binding is made. And it's an annotation-based mechanism. We leave notes in the code to determine what to include. So CPP, like I said, is mainly used for C and C++ development. It gives us means for file inclusion, lexical macros, and conditional compilation. And together, these three things enable the implementation of variability. So if you develop in C or C++, then you've seen the use of at least this pound include directive as a way to import functionality from another file, right? So for example, in the slide, pound include string.h, right? This is a directive that says, hey, import the code from the string.h header file. And that gives me access to it in my program, right? So CPP is going to see this, and it's actually going to bring in that code directly when it compiles, right? And that's how you import. Macros are defined with pound define, right? When you define a macro, the preprocessor is going to replace all occurrences of that corresponding token with a different token sequence. So, if we define something with a name, feature name, and a value, and just generally we just use true for if we're including it, and we don't define it if we aren't including it. It's every time it sees that feature name, it's just going to substitute in true, right? If we don't define this, it's going to say, hey, that's not defined, and it's going to then use that to ignore the code that we're not including for the features we haven't selected, right? So after you define a macro, the preprocessor replaces all the occurrences of that token with the different token sequence. These serve as compile time variables and functions. They can be defined and redefined and undefined while we preprocess the file. So to implement this in the product line, we reserve a name per feature. Usually that's the name of the feature. And we define the macro only when the feature is selected. We do not define it if it's not a selected feature. So finally, this enables conditional compilation in conjunction with this if-def and end-if, right? And if, just plain if. So if-def says, hey, if this macro is defined, then we're going to include this code. If it's not defined, we're going to ignore this code and strip it out, right? So this is going to check whether macros are defined or not. We define a feature if we're using it. It sees it is defined, it evaluates to true, and that code is included. If it's not, then it's excluded. Okay. So here we have an example. And like I said, this is actually some Java code. This actually isn't C code. It just is a useful example. But it basically is the same thing we would be doing otherwise. We have three features: name, no name, and color, right? And we check that those are defined by checking that there is a macro with that name defined. So if name is defined, this code is included. If it's not defined, we strip it out and ignore it. It can also, with if, we can also check any user-defined condition, but we generally keep this simple, and we just define a macro for any used feature, and skip this for features not included, right? All right, so here's an actual C example too, from a database implementation. In addition to if-def, where we also have this if-end-def, that's if not defined, we'll include this code, right? So if we're not using the feature have queue, then we include this code. We of course have else, right? If this is not true, we do this instead. I didn't include it here, but we also have an elif, right? And we can nest, of course, these particular directives, like line 17 ends the one on line 5. So we have an else, and then within that, we have another if-def inside of the else part of this, right? So there's a question in the chat. Would it be bad to simply assign it to false if it's not included? The thing is that you could do that. You won't use if-def. What you would just use is just use if, right? And you could do that. The if-def and if-end-def specifically check to see if something is defined or not defined. So that's why we do it by only defining the included one and ignoring the other ones. You could implement this using true and false instead. Then that way you already have a list of macros and just swap those. No matter what, you have a manual element where you need to go in and note which ones are either defined and not defined, or note which ones are true or false. But you could do it that way. It's just more common to do it the way with the if-def and only defining them. Any other questions on this? Okay, so CPP is the standard way in a lot of cases to compile C and C++ code. So those capabilities are kind of innate to C and C++ development. You're unlikely to write code in either of those languages and not have the ability to implement variability in this way. So that's why, or one of the several reasons why, if you're developing in C and C++, preprocessor-based implementation of variability is pretty standard. But like I said, that's often because those are things used in embedded systems development, right? Where you really need those tiny optimal executables. In other languages, you don't have as native of a manner. Like Java doesn't have a native manner to control conditional compilation, but there's external tools we can use to enable the same options. One of the more common in Java is what's called Antenna. Antenna was a preprocessor that was originally designed for Java Mobile Edition. And when that first came out, it was another case where it was, again, very essential to build small, lean executables because you were usually developing for devices with very limited capabilities. And so Antenna has existed for quite a while, but it is a way that you can perform preprocessor implementations. Oh, and there is a note in the chat that if you just say define foo, yeah, you don't have to have the true either. That's optional. That's exactly true. Okay, sorry, got distracted there for a second. Antenna is an external tool, right, that operates in Java code that can be used with any number of code editors or can integrate into your existing build process pretty simply. It mimics the syntax of the C preprocessor, but preprocessor directives are written in comments, right? So they don't interfere with existing code editors. Instead of removing code fragments, Antenna comments out code fragments that are annotated with deselected features. So if the feature is deselected, it goes through and it comments everything out and then runs the compiler. And that way developers can edit Java code in their normal code editor and then quickly switch between different feature selections. The code is changed in place through this commenting system and is not generated in separate files. Antenna can be used from the command line, or it's also integrated into different code editors like Feature IDE, which you're going to use in assignment 2. It also incorporates Antenna as a way to define a project. Antenna uses a similar set of directives, the CPP, to annotate the code. It uses if, elif, else, and end if, right? So again, in the same manner, we start in it with if feature name. If we include this feature or we chose this feature, it will include this code. We have an elif, right? If this other feature is chosen, include this code instead, else, and so on, right? This is pretty straightforward, just like with the CPP examples we've shown. Antenna uses comments for deactivation of the code, which are specifically the 2 forward slashes, then an @ just to specifically note the ones Antenna has edited. So it's possible for Antenna to use the same files as input and output to cleanly transform code. All right, so we have a couple of examples here. The example on the left, we've enabled the features hello, beautiful, and world. We have not used wonderful, so that's commented out. The one on the right instead uses hello, wonderful, and worlds. So beautiful is commented out because we haven't enabled that. So it prints hello, wonderful world. This one prints hello, beautiful world, right? Now, preprocessors are fairly powerful tools. They allow almost arbitrary source code manipulation at compile time. That power comes at the price of writing complex and hard to maintain, hard to understand source code. So, just like the goto statement, preprocessors sometimes have a fairly poor reputation. Preprocessors can align with your underlying code structure, but they don't necessarily have to. For instance, you could annotate either an entire block of the source code, like an entire function or an entire statement, or you could wrap a partial statement or a partial function. And the latter is not really useful because that can lead to situations where you try to compile code with only a partial statement. Right, so you want to be really you want to be really careful. The examples up here on the top in this slide are proper ones. They wrap around the top level declaration on the left, right? And on the right, an entire statement, at least this entire if block is within this if def. The one on the bottom are more problematic because they wrap partial expressions. For example, this one here, right? You don't know the value of this decides whether line 8 here, this if n equals 0, is within the body of a for loop or not, and that's potentially very problematic. That could cause you to miss major issues in your code. Right, so you want to be really careful when you're using these. On the positive side, preprocessors are very lightweight. They're very easy to use tools for compile time variability. They're already available in a lot of language environments, or pretty easy to integrate with external tool support like Antenna and Java. They have a very simple programming model. Annotate and then conditionally remove code, right? Just that way you can just strip away code that's not easy to use. A lot of developers, especially C developers, are already going to be familiar with these. You've probably already worked with macros, even if you haven't used them in the same way, right? And they are very lightweight tools that you can add into development. You can apply these preprocessors uniformly to artifacts of different kinds too. There are cases where you can apply them to non-code or non-text artifacts as well. Right? So you can use often the same variability mechanism for your source code, your models, your documentation, and so on. That allows changes arbitrary levels of granularity and not just confined by the mechanisms of your programming language. Since most preprocessors are fairly simple, it's usually easy to extract your feature to code traceability or linking between the feature and where it is in the code, right? And this is also a suitable way to move from a non-product line approach to one where you become a product line within your code base, because you can add some preprocessor directives to your existing code and add more over time and refactor over time. So this lightweight, easy to learn, easy to adopt nature of these makes them very popular in practice. They have some major drawbacks though. Feature code is scattered across the code base. It's often mixed with code of other features. There's no real support for encapsulation of features separate from other features. And even when code is roughly separated into distinct files, annotations are scattered across them and remain to inject code into feature code into the base code. And that scattering makes it hard to understand the code, and it makes it hard to know how to configure that code, right? Preprocessors often lead to quick and dirty solutions where rather than refactoring and restructuring the code properly, you just sprinkle some of the more of these directives in there and hope it works, right? And that can lead to implementations that are hard to understand and hard to maintain. They are not typically part of the language itself and are often added on top by an external tool, which means that the code itself can be often really hard to follow once you start adding these in. Right, so these can get very confusing very quickly. Overall, preprocessors are a great simple means to implement variability, but have several dangerous pitfalls. And if they're used sparsely in a disciplined fashion with suitable tool support, a lot of problems can be avoided, and they're a great approach, but they can also get very confusing as well. Right? Now, the second approach I wanted to talk about today, and we don't have much time, so we're going to go pretty quickly, but there's not really a lot here. This is a super simple approach, is what we call the parameter-based implementation, right? And there's many ways to implement variable code using the mechanisms of your programming language that have been used long before the invention of a product line. Like I said before, even a simple if statement gives you a choice between different execution paths, right? So an if statement is a way that you can implement variability. You can say, if this feature is enabled, do this. If this other feature is enabled, do this, etc. Right? To prevent cluttering your code with if statements, to enhance your feature traceability, right? To find the feature where the feature is implemented in the code. To provide compile time or load time variability, developers have identified a bunch of common programming patterns to support variability, including parameters, design patterns, frameworks, and components and services, right? And we'll talk about all of these, but these are really your foremost well-known and commonly used ways to implement variability. Most industrial product lines are implemented with one or more of these often mixed together. working in combination to enable controlled variability, and each has its benefits and downfalls, right? So the simplest of these is parameter-based implementation. It's to use conditional statements like if and switch to alter the control flow of your program at runtime based on the selections you've made for each variation point. In our context, conditional statements are usually controlled by the configuration parameters that you either pass to a method or a module of your code, or those you set as global variables in your system, right? Different parameter assignments lead to different versions of your code executing, different configurations of your program when it's been run. There's different ways to set your configuration parameters. In general, what we'd expect is one Boolean parameter per feature, right? Either set globally or at some appropriate level of scoping. And those variables should be named ideally in a way that directly maps to your feature model. Often command line parameters or configuration files with a set of options are read in at startup of your program. And then you set the values of those Boolean variables and then run your program, right? And that would be an example of load time binding. We make decisions when we run the code by passing in our choices from the command line or using some kind of configuration file. In other cases, users could change parameters using a GUI during runtime and change the situation or the system while it's running, or as part of an API request. Like, like I said before, maybe make a post request to your REST API with a set of options that should be used. And sometimes it has immediate effects in terms of runtime binding, or other times it's going to require a restart, so a form of load time binding where we restart the code with the new settings. So the use of parameters is a fairly flexible approach, simply noting in the code how to make use of those parameter settings. So this is pretty simple, and it has its benefits and drawbacks. So we've got a graph example with two configurable features, weighted and colored. Those are implemented as global configuration parameters. We have this class conf that stores the values of them. And somewhere else we have code that sets them. So when we read in command line options, we then set the values of these, and then we use those values throughout the program. Right. The parameters are evaluated inside if statements in graph, in the graph class, in the node class, in the edge class. We check the values of those, and then we run code conditionally based on the values we set. Like I said, very straightforward. Right. Now, implementing variability with parameters is pretty straightforward. For that reason, it's pretty, it's widely used, right? Everyone writes if statements. Variation is evaluated at runtime when these conditional statements are executed. And this approach shares the general benefits and drawbacks of runtime binding. For example, all the functionality is included in all the deployed products, even if we know that feature is not going to be selected in general, which has potentially negative implications for resource consumption, performance, and security, right? That deactivated functionality is still in the product. Performing runtime checks, those if statements, requires additional computing overhead that you wouldn't necessarily have in a version where you compile it only with the selected features. For instance, in that example in the last slide, even though we know we'll never use the feature color, the application still contains the class color. It evaluates an additional if statement whenever the print method is called. It requires memory for an additional field of every node and edge object, and that can add up. And we cannot prevent others from instantiating objects or invoking methods of deactivated feature code other than throwing runtime errors. So shipping unused code opens unnecessary potential targets for attack, like buffer overflow attacks, right? So there's risks included in this approach that you don't necessarily have in the compile time approach. It is possible to alter feature selection without stopping the program, right? But runtime changes are non-trivial in general, and the features code may depend on certain initialization steps or assume certain facts to be true, and those could be violated if we let the program change at runtime and we're not careful. For example, we might run into a null pointer exception if we enabled wait at runtime because the field weight of the previously created edges was uninitialized and now has a null value. In those cases, it might be easier to require a restart of the program when those configuration parameters change rather than letting it attempt to continue at runtime. An advantage of passing configuration parameters as method arguments is that different parts of the control flow can be configured differently. So we can use colored graphs and uncolored graphs in the same program. So that's one good side of this. Conditional statements to the source code can be considered a form of annotation. We're marking our intentions. We're marking the boundaries between features within the code. I know it's 3 o'clock. We're going to talk for just a few more minutes. We're nearly done. So stick with me, or if you have to go, check the last few minutes of the video later on. Annotation with conditional statements are available at a fine granularity. So if statements, we can change the program behavior at the statement level. Configuration parameters can be encoded in essentially all programming languages, but they're usually not applicable to non-code artifacts. That's a downside to consider here. Preprocessors, to some extent, can be used on non-code artifacts like your documentation. If statements are specifically a programming language construct, so they're harder to use for other artifacts. That's something to keep in mind. Another thing to keep in mind is that configuration parameters can lead to implementations with poor code quality. Like on the one hand, global parameters are tempting, right? They're just there, but they reduce modularity. They reduce the ability to break the code into independent modules. On the other hand, sending the set of these Boolean values to every single method that uses them is also not necessarily a good approach. You might instead want to pass around the single configuration object that encapsulates these options. Finally, one more thing to mention with the parameter approach is that variability-related code is going to be mixed within your code base often. You might have feature codes scattered across different files and different classes, different packages and modules, stored in variables in different places, and method arguments and if statements and so on. So it can be hard to understand the code, right? Versus an approach where feature code is specifically encapsulated in its own classes. In addition, feature code is tangled, it's tangled within the code base and the code of other features. It's hard to understand and specifically identify all code related to a particular feature if you're not careful, right? That can make maintainability and understandability of the code really, really difficult. So it's often better to use, you can use if statements for selection, but be careful and make sure that your feature code to the largest extent possible is self-contained and then plugged in at the appropriate point. And next time we'll talk about, at least some ways of doing that. So parameter-based approaches are easy to understand and use, and they're very flexible. They allow different configurations in the same program, but they mean that your executable has all the code encapsulated within it already. And that leaves you open to security attacks. That means that your program requires more memory to run and has more overhead from checking at runtime all these different options. All right, it can also be hard to understand the code base because your feature code can be scattered all over the place. Are there any questions on any of this? Right. So how we build a custom product from a feature selection is something that we look at across these 3 dimensions of the compile time. When you make decisions, do you make them when you compile, when you run the program, or can you freely reconfigure the program at runtime? Do you use language mechanisms to implement this, or do you use tools external to the code? And do you use a composition-based approach where features are contained in independent pieces of code? Or do you use an approach where you simply make notes within the code saying this code belongs to this particular feature, right? Preprocessors are a compile time tool-based annotation-based approach where we selectively remove code that we're not using when we compile it based on notes within the code. Parameter-based approaches simply use if statements to execute code selectively based on information choices we pass through the command line or at runtime through a GUI or API requests. All right, so that's all we've got today. I'm happy to answer any more questions, especially since I had to rush through a little bit at the end. Next time, we will talk about implementing using design patterns, right? Which is generally a load or runtime-based approach using the mechanisms of the language and based on composition where we try and separate feature code out independently. There is a question in the chat. Do these have to be Boolean values? Not necessarily. Most of the time it's a yes or no, but you also often have choices where you have non-Boolean values as well. For instance, you could configure a program's parallelization approach based on the CPU you're running, right? Where the number of threads you split the program to run over depends on the particular CPU, and that's a non-binary configuration option, right? That's, you have this many threads to work with. So these don't have to be Boolean. It's just we're using Boolean for simplicity, and a lot of times it's yes or no. We're using this particular option, right? For a case where you have multiple options, each of those are their own features. Right? So for instance, there's another question where if you have a robot that has multiple strategies for dodging. Well, that's exactly what you would look at in the feature model, where you have different selections you can make. These are each strategy is a feature, right? So I off the top of my head, I don't know what the different strategies would be, but like let's say that you had a sensing strategy where you could use a radar, a LiDAR, or a camera. So you have three options, right? Those are three features. So in your feature model, you would then say you could either select only one of those, or you could select one or more of those for the sensing parent feature. So there's a parent sensing and then three children, LiDAR, radar, and camera, right? And then you can use one or more of those in your model. So there's mentioned might use one strategy for one versus one and another when it's more, right? And again, those are different features. They have a parent feature called dodging strategy. So let's see if I can, come on, I was trying to get the Zoom window up. All right, so here's an annotation. Let's see, and I can draw. All right, let's see. All right, there we go. Cool. So in a feature model, you would have something for, right, and this is your dodging feature. We'll just call it D, right? And then we have 1v1 is a feature, right? And then maybe 1v2 is our alternative, right? So this is what it will look like in your feature model. These are different choices you can make. You could use the 1 versus 1 strategy. You could use the 1 versus 2 strategy. And then this could be either the empty circle where you only choose one of them, or it could be the filled circle where now you can use one or more of these, right? Now, similarly, you could do this differently where they're entirely separate. And where's my eraser? There's my eraser, right? And so rather what you could do as another approach to this is that you could say, 1 versus 1 is mandatory. You have that filled circle. And 1 versus 2 is optional, that empty circle. And then you always have 1 versus 1 strategy. And sometimes you can also choose to include that strategy. Does that help clear that up a little bit? So, okay, pose the question a little differently. Sorry, the person in the chat who asked the question originally says that they're gonna. Okay, there we go. He says he's posting a little differently. So for one robot moves, it uses the orbital movement first. If it gets hit too much, it switches to oscillation movement, and if it gets hit again, it switches to ramming. Okay, so that count as one feature or as three different strategies. So this is. I would say that those are three different features, for example. But it's not necessarily so this is something the current code, yeah, and some robot, yeah. So you have a concrete one that your concrete product chooses how it mixes these. And so when you're modeling this in the product line, those are three different features, but some robots use them differently, and that's fine. The code itself and the robot chooses them. That's not necessarily something in your model, but we'll see here. Basically, let me erase this a little bit. All right. Right, and just ignore the names for these for now. Right, let's draw this in. So we have three strategies. These are three features, right? It's not a matter of choosing necessarily one or more, but what you look at is across your product line, how are those used by different robots? Do all of them use all three? If for example, all of them use the orbital one, then you'd have this filled circle, this mandatory option, and saying that, if all of them use orbital movement, then that's mandatory. That's always included, regardless of which robot it is. Now, if you have some robots that use this second strategy, if some robots use oscillation and some use ramming, then those are optional features, right? Those have that empty circle. So what you're saying is that, some robots would include all three of these. Some might only include this one. The order doesn't matter. How they use them doesn't matter in this case, right? The concrete product can decide how it uses them. But you have some kind of movement strategy, right? And that's this parent feature, is that you have some kind of movement strategy, and it can break down into one or more of these. Now, it's definitely not a case where you'd only choose one, right? Because you have robots that use all three of them in different ways at different times. So it's possible to choose all three of those. Does that help clear it up a little bit more? Great. Cool. Now, there's also a separate question asking if there's any approaches which combine a composition-based approach and compile time binding, right? Where basically where you have code, the feature code is separated and independent, and then at compilation time, you only bring in the correct units. I don't have a great one off the top of my head. I'd have to think about that a tiny bit. I imagine there's something though, right? Some kind of approach where you just select. Actually, I can kind of think. You might have something where you have like a build script, right? And your build script selectively compiles certain independent modules together when you compile, and that would be an approach that's composition based in compile time, where the code is separated into distinct units and the build system selectively compiles certain elements together, right? So that would be one way you would combine those. There's another question. Would it be of any value to have a separate feature that says something like change movement on hit? That might be something where if you have different strategies for how you change the movement on hit, you'd have a similar kind of model. The parent would be movement change on hit, for example, and then you'd have different strategies for how it does it that you select from. Okay, so there's a follow-up again from the original person who was asking, Emmanuel. And they're asking, they don't fully understand how you can translate this to code if you can't communicate how the different robots use the same selection differently. And if this is an example where we can't generate the code automatically. Yes, that's correct. This will be a case where you could not generate that automatically, right? The automatic generation is in cases where these can be treated as dependent and distinct and separate, right? But if you're merging these in different ways, that's something that you would be coding by hand still, right? That's not something that's automatically generated from your model. Yeah, there's a question. If antenna comments code depending on the variant selected, will it not make diff messy? Get diffs messy and hard to read? Yeah, absolutely it will. Antenna does not necessarily play nicely with Git. You have to be really careful with that. Because you're selectively commenting out code. If you then commit that back in, that might conflict with someone else who has different code commented out or who doesn't have that code commented out. And it is going to mess with diffs. You have to be very careful with preprocessors like Antenna, right? So that's something to absolutely watch out for, because that can play havoc with diffs, with Git diffs, with integration into version control and Git in general. So just you keep it, watch out for that if you're working with preprocessors. Cool. Are there other questions? Then that's all I have. We'll go ahead and wrap up there. Feel free to email, ask questions on Canvas, talk to your supervisors, any of the combination of those if there's more that you're not clear on, especially as you start assignment 2.